We're going to talk about E now. E is like this irrational number. It's this rational number that's kind of like pi. So if you plug it into your calculator, there's actually a button for it. It's actually 2.718 and it goes on forever. If you ever wondered what this button right over here is, this ln sign, this is actually log base E. There's also, on the calculator, there's also e to the x, right? So it's pretty clear that E has kind of a lot of usefulness, right? It has to have some meaning to it. But before, we can jump into all of that, we gotta see where E comes from. And before we do that, we have to talk about interest. Interest is the price of borrowing, or the reward for saving money, or even the price for lending money to people. So if interest, it's kind of weird because it allows you to earn some extra money. So let's say, your friend wants $1, you give him $1, and then the next day he has to pay you back $2. So interest allows you to kind of make some extra cash if you're lending money to people. So let's give an example. Let's say I let this guy borrow $10, and every day he does not pay me back, there's a 10% interest. Now, there's two types of interest we're going to be looking at. All right, so this kind of depends on the type of interest we're talking about. There's simple interest, which you can think about as linear growth, or there's compound interest, which you can think about as exponential growth. Let's get into linear growth. So we said that we wanted 10% interest, right? And in this case, this 10% refers to 10% of the original amount that we had. So in this case, the original amount we had was $10. So 10% of $10 is 1. So every day that he does not pay me back, he has to give me an extra dollar. That's basically what simple interest is. It's a linear growth, right? Every day it's always $1 and an extra dollar he has to pay me back. So on the day that I gave him the dollar, he owes me $10, and then if he doesn't pay me back on the next day, he owes me $11. If he doesn't pay me back on the next day, he owes me $12, and you kind of see the pattern, right? So it's just 10% or whatever percent of what you originally had, and you keep adding that day by day or month by month, whatever kind of time period you're doing. Now we have compound interest. This is a little bit different. So you can think about this as interest on your interest. It's exponential growth. So you're paying interest on the original amount and on the new interest. So this sounds really weird, but we can take a look at an example. So on the 0th day, obviously, he owes me $10, right? Then on the next day, it's 10% of what we originally had, right? So we had $10 at first, then he pays 10% on the $10, so he owes me $11, right? It's the same step as this, but then something weird starts to happen. Then on the 2nd day, he owes me $12.1. This 12.1 comes from this. So basically what happens is, now you take this new value and you apply 10% to it and you add on to the new value. So instead of in the simple interest, you notice how it's always the same value every time, right? You're always taking interest on the original amount. But now in compound interest, what happens is you're taking interest on every new amount. So every new number, every new kind of cycle that you go through, well, you're going to be taking interest on that new value. So the thing you're taking interest on is constantly changing. So in this case, you're taking interest on $11 this time. So 10% of 11 plus 11 gives you 12.1. And then now you're taking 10% of 12.1. So you're taking interest on this new value and you're adding it to 12.1. So you get 13.22. The next day, you would take interest on 13.22. You would take 10% of this, add it to that amount, and then you get a new value. So compound interest is just you're giving interest on kind of every new value that you have. It's not just interest on this one thing, it's interest on kind of everything. Now, where does E come from? Let's say we start off with $1 and there's 100% interest. And I want to find out how much money can I earn as I compound this more and more per year. So if I compound this one time a year, well, I'm just going to get 100% interest, right? So then 100% of 1 is 1, and 1 plus 1 is 2. So at the end of 1 year, I'm going to get $2. Now let's say if I compound this 2 times. So what's going to happen to the interest is it's still going to be 100% interest, but because I compound this 2 times, I'm going to break the interest up into two 50% parts. So it's going to be 50% and 50%. And notice how 50 plus 50 gives me 100, right? So it's still 100% interest. I just broken it down into two parts. So 50% of 1 is obviously just 1.5. And I take another 50%, so 50% of 1.5, that gives me 2.25. If I compound this 3 times, now I break it up into 33.333% sections. So on my first compound, 33% or 33.3333% of 1 is just this. 33% of whatever this number is, that's going to lead you to 1.773 repeated. Then 33% of this value right over here, because remember, it's compound interest. So the thing that you're always taking interest in is always changing, right? You took interest in this, now you're taking interest for this number, and now you're taking interest for this number. So 33% of this is going to lead you to 2.3053 repeated. And what happens if you compound this infinite many times, right? Because it seems like if we compound this more and more, we get a bigger number, right? We originally got 2, then 2.25, then 2 point whatever this number is. So it seems like if we compound this more, we get kind of a bigger number. So if we compound this infinite times, we actually approach 2.718, which is E. All right. So this is where the number E comes from. This is when you take this kind of problem and you compound it infinite amount of times, and you get this number. And you can actually model this using an equation. So if y represents the total amount of money I gain after all the interest, and x represents the amount of times that the interest is compounded per year, and you can plug in values for this equation, right? So if x is equal to 1, that means I compound this thing one time a year. So I get y is equal to 1 plus 1 divided by 1, which is just 1, to the first power, and I get y is equal to 2. And you notice how when I compound this one time, I get 2, right? If I compound this 2 times, I get y is equal to 1 plus 1/2. And notice how it's to the second power. So we're compounding this 2 times, right? So I'm going to get 2.25 if you put this in your calculator. And, well, that matches up with what we have. So this equation model is basically what I just written up here. And just a fancy way to say it is, as the limit of x approaches infinity for this function, basically, as we make the amount of compound, in this case, x value, approach infinity, so we're doing this kind of infinite many times, well, it's going to approach this value, which is E. So yeah, that's basically just a fancy way of saying that, what we originally said here. Now we're going to talk about applications for E. So we learn what this number is. Why is it useful? And the reason why is, well, we can model exponential growth and decay using E. Now you might be asking me, I did this in my Algebra 1 middle school. That's easy. Modeling exponential equations is y is equal to a times b to the x power. And it will be right. But another way you can actually model exponential growth or decay, is y is equal to a times e to the bx. A represents the original amount of the thing you have, b represents the growth or decay rate, and x represents the time. And y can represent the total amount of kind of money you gain after interest, or if you're modeling population, it can model kind of the final population. So yeah, and say if we started off with 100 people and the population grew by 1% per year. So how many people will we have in 1 year? Well, I mean, in this case, you could just use the original exponential equation. So you can be like, okay, this is equal to y is equal to, let's see, your original amount. So the original amount of people I have is 100. And we're growing by 1% each year. So this is kind of the same thing as we have 101% of the amount that we originally had. And we're raising it to the x power, which represents time. And since this is measured in years, and we're trying to find out the amount of people in 1 year, well, our exponent, our x, would just be 1, right? Our time passed would just be 1 year. And it's just equal to 101 people. Seems easy, right? But what if, no, that was a horrible voice crack, but what if I wanted to find the amount of people in, let's say, 1.12 years? What if I wanted to find the amount of people in 1.22239 years? And that's the case when you would use the formula I showed you right now. Okay? So the first formula, it's good for kind of when you're doing things monthly, annually, yearly, every year or every 2 years, whatever. But this formula is good for when you're doing things in kind of like a chaotic way, like a chaotic time. So in this case, 1.222 whatever 9 years. This is good for measuring kind of weirder kind of time periods, instantaneous kind of time periods, like instantaneous changes in the population. So let's put this. So let's say if I had 1,000 people, and my population grew 3% per year. So how many people would I have in 2.25 years? And I would use this formula. Now keep in mind that this growth and decay rate right over here, this is a little bit different than what we do in the other exponential equation. So you'll see. So if let's just do it in let's just compare the results actually. So I'm going to first do it in the original equation, and then secondly, I'm going to do it in my new equation and kind of see the differences. So my first equation, it's a bit simpler. It's just y is equal to my original amount times the growth rate. In this case, growth rate is 3% per year. So that's going to be 103% of what I originally had, right? Originally, I started out with 100% of my kind of population. If it's growing by 3% per year, well, then it's going to be 103%, right? So it's 3% plus this 100%. And it's to the x power, which represents time. So in this case, my time is 2.5 years, 2.25 years. And I'm going to get 100 times 3% to the 2.25. I get about this. And then 0.84. Now, for my second method, I'm going to use the other formula. I'm going to use the new formula. So it's going to be y is equal to our original amount. So notice how it's the same. But then I introduce the e. And now for the b part, in this case, for my second equation, I actually don't put 103%. I only put 3%. So that is a big difference you got to remember. All right, you don't put that percent plus 100%. You only put the percentage itself, if you know what I mean. Right, it's 3% per year, so you're going to put just 3%. You're not going to put 103% like you did in the first equation. And it's 3% times 2.25, which is the time. So you'll get 1001 times e to the 3% times 5, and you get this 0.9. So you notice how when you're using the second formula, the result is a bit bigger than what you have when you're doing the first kind of problem, at least when you're doing exponential growth. All right, and this is because it accounts for kind of those tiny changes, right? This equation, we said how it was good for, let's say, 1 year or 2 years, 3 years. But then when you get into those tiny changes, then this other equation gets more accurate. Now let's talk about half-life. Half-life represents the amount of time it takes for half the nuclei in a sample of atoms to decay. So atoms are the building blocks of the universe. If you take in chemistry, well, you're in luck because you probably already know this. If you just take in biology, you probably think, cells are like the building blocks of life. But atoms are literally like the building blocks of the universe. They're smaller than cells. They make up everything. So nuclei represents kind of the center. You can think about it as the center of the atom. And atoms, they often go through decay. They often go through decay over some type of period, some time period. And the number in this case, right, we start off with 100% of our nuclei, right? Because half-life represents the amount of time it takes for half the nuclei in the sample to decay. If there's 0 half-lives, aka if 0 time has passed, well, none of the nuclei would have decayed. After 1 half-life, well, you get down to 50%, right? It's the time for half the nuclei in the sample to decay. So after 1 half-life, well, half of the nuclei would have decayed, right? So you would have gotten 50% of the original amount. Then the second half-life, it's time for half nuclei in that sample to decay. So it's going to be half of 50%, which is 25%. Then after the third half-life, well, it's going to be 12.5%. And you see kind of the pattern, right? It's always half of half of half of half. And you notice how the ratio between kind of one half-life and the half-life before it, or the number of half-life before it, it's always in like a 1/2 ratio, right? You always have 1/2 of the amount that you had from the start. Now, sadly, I said that there was like an exponential formula for like the new E kind of we learned, but that's for representing growth. So for exponential growth, you use the formula I showed y'all before. But when we were talking about exponential decay, which is, half-life involves that, well, all you have to do is just put a negative sign there. So for exponential growth, you don't have to put any sign here. It's just e to the bx, a times e to the bx. For decay, it's a times e to the negative bx. That's the only difference. Now let's put things to use. So the half-life of a certain radioactive substance is 1 year. If you start out with 100 grams of the substance, how much of it will remain after 2.5 years? So one problem you might notice when encountering the question is you don't know what the growth rate is or the decay rate is, right? If we use our decay formula, right down here, it's y is equal to the original amount. In this case, our original amount is 100 times e to the, we don't know what our growth rate is, but we know our time is 2.5 years. Now, how do we solve for our decay constant? How do you solve for k? Well, let's just start off with our original exponential equation for decay. And let's divide both sides by a. So we get y divided by a is equal to e to the negative kt. Now we know that after one half-life, we know that the ratio between the half-life and what we had originally, we said the ratio was 1/2. And in our exponential equation, if you remember, we said that a represents our original amount, our OG amount. And we said that y is equal to the new amount. So after one half-life, the ratio between the new amount that we had and the original amount, so the new amount to the original amount, that has to be 1/2 after one half-life. So y over a, in this case, the ratio between these two numbers has to be 1/2 after one half-life. And in this case, one half-life takes 1 year, right? One half-life takes 1 year. So for time, we can plug in 1. So e to the negative k times 1. So we kind of made like a new equation to solve for k. Now, in order to solve for k, negative k times 1 is just negative k, right? What we can do is we can take the natural log of both sides. And in case, you need a little review on logarithm properties. I mean, we kind of just learned ln, so, this step might not make a lot of sense. But basically, ln is log base e. And for logarithm properties, if you have log base b of, let's say, b to the a, you're going to end up with a. So in this case, if ln is log base e, and we have log base e of e to the negative k, well, we're just going to be left with the exponent, in this case, negative k. So we got rid of the e part. So we're going to get ln of 1/2 is equal to negative k. And if I divide both sides by -1, I get that negative ln of 1/2 is equal to k. Now this, you can just plug in your calculator. So negative ln of 1/2, that's equal to that's about 0.693. All right, let's just say that, 0.693. So now we know that k is equal to 0.693. So now we can plug it in back into our original equation. So 0.693 here. And now we could just plug the rest of this into a calculator. So we have 100 times e to the negative, because remember, this is decay, right? So this is negative k. My bad, I didn't put the negative sign there. So negative 0.3 times 5. And we get 17, we get about 17.684 grams of our substance remaining, right? Because we started off with 100 grams, and then now we end off with 17.684, and remember to write grams as your unit, right? And yeah, that is the answer. So, when you're doing half-life problems, it can be tricky, but just know that, the ratio between your kind of final amount and your original amount for a half-life equation is always going to be 1/2. And you can use this ratio to your advantage by substituting it into this equation. And after that, solving for the constant using natural log, ln. The half-life of a certain drug in the body of a patient is 8 hours. If a patient is administered 200 ml, how much will remain after 1 day? Immediately what I notice is that our unit in time is hours, right? But the problem is, it's trying to find out how much will remain in 1 day. So the units are different. So just to make everything clear, instead of 1 day, I'm going to put 24 hours, because it just makes things simpler, right? Now the units are the same. Let's plug in what we know. So we know that we originally had 200 milligrams. It's going to be e to the negative k times the time in hours. So we have 24 hours. So we're going to put 24 here. And now we can solve for k. We know that, once again, I'm going to just divide a by both sides. So I'm going to get y over a is equal to e to the negative kt. Now, we know that the ratio in 1 half-life is 1/2, right? And 1 half-life occurs after 8 hours, right? 8 hours, that's when the ratio between our original amount and the new amount is 1/2. So now we can solve for k by taking ln of both sides. So this cancels out with e, and I get ln of 1/2 is equal to negative 8k. I divide both sides by negative 8, and I get that k is equal to this thing divided by 8. Put this in the calculator. I'm going to get ln divided by negative 8. I'm going to get 0.0866. All right, I'm just going to round it to 3 numbers down. I mean, it's 4 numbers down, but 3 actual numbers besides 0. So my k in this case, k is equal to this, which means we can substitute it into this equation. So if I substitute it all the way up, I'm going to get negative 0.0866 times 24, and now we can just put this into our calculator. So 200 times e to the negative 0.0866 times 24, and we get about 25.026, 1.1, and don't forget the units, so we will get milligrams. And there we have it. That is the answer. And notice how we could have actually done this in a simpler way, right? Notice how 8 is a multiple of 24. So I'm actually going to write this here. So if we originally had 200 milligrams, after 1 half-life, which is 8 hours, we're going to get 100 milligrams, right? Because that's half the amount we originally had. Then, after another half-life, which is another 8 hours, so 16 hours in total, right? We're going to get 50 milligrams, because that's half of 100. And finally, after another 8 hours, so in total, this is 8 plus 8 plus 8, which is 24 hours in total, which is 1 day. We are going to get 25 milligrams. So, yeah, notice how it matches up, right? This matches up with this simpler way of doing it. So, yeah, that is how you use E for exponential equations.